Hello students, now we are going to discuss new chapter current electricity. So we already well known about electricity. Without electricity we are not leading in our life. The previous chapter electric charges and fields, electric potential and capacitance. From these chapters we have to discuss only static condition of the electric charges. So this topic we are to going about electric current, Ohm's law, and resistance of a material of a conductor. So these things we have to discuss when the charges are in motion. From this chapter, the important concept is electric current. So here, what do you mean by electric current? The electric current is defined as the rate of flow of charges through any area of cross section of the conductor. So that is nothing but electric current. That means when the charges under in motion in a conductor, so that is what we call electric current. It is given by I is equal to Q by T. I is current, Q is the charge, T is the time. That means it is the ratio of charge by time. Okay, so that is what we call electric current. This electric current we can be divided into two types. One is direct current. We well known about DC current. Another one is alternating current, AC current. DC means that means DC direct current whose magnitude remains same with time. Another one is alternating current. The magnitude changes continuously with the time and the direction changes periodically is known as alternating current. So this is what we can divide into two kinds of electric current. So next another is instantaneous current. It is given by I is equal to dq by dt. At a given instant of time, what is the quantity of current flows through the conductor? So that is what we call instantaneous current. So the current, electric current, nothing but charged by time. So the SI unit of electric current, because of electric current is a quantity. This SI unit is ampere. It is denoted by letter A. So this ampere we can be defined as if 1 coulomb of charge flows in 1 second across any cross section of a conductor, then the current is said to be 1 ampere. That means in 1 second the current flows across any cross section area. That is what we called 1 ampere. That means 1 coulomb of charge flows in 1 second, any cross sectional area is said to be 1 ampere. So this is what we call 1 ampere, isn't it? So this electric current is a scalar quantity because of it having only magnitude, there is no direction, isn't it? But it having the direction forward and backward direction, so here it cannot be depend, isn't it? So that the electric current is a scalar quantity because of there is no direction, only magnitude. So it can be expressed 1 ampere is 1 coulomb by 1 second. So that is we can call it as 1 ampere. Usually the current we can measure milliamperes, microamperes. So what do you mean by 1 milliampere? That means 1 ampere of current is divided into 1000 times, then we said to be 1 milliampere. So this is a unit of electric current, that means 1 ampere. So next thing is current density. Okay, that means what is the density of current? That means the electric current per unit area normal to the direction of current is known as current density. So it can be written as J is equal to I by A. I is equal to electric current, A is area, isn't it? The SI unit of current density is the ampere per meter square. So this is what we call current density. The unit is ampere per meter square. So next, the important concept or the very familiar in our physics, that is the Ohm's law. This Ohm's law, current is directly proportional to voltage. So that is easily we can say it. That is what we call the Ohm's law. The Ohm's law states that the current flows through the conductor is directly proportional to the potential difference applied across the ends. That means, so here this is the conductor. Okay. So what is the potential we have to apply? This is the battery. So that potential is V, and L is the length of the conductor. This is the one end. This is the another end. A is the cross sectional area of the conductor. What we are considered the diagram. Okay. Here V, what is the potential applied across the ends of the conductor, and what is the current developed to this conductor, isn't it? So here the current is depends on the potential difference. So that here the statement states that the current is directly proportional to the potential difference applied across the ends, isn't it? So that is what we call Ohm's law statement. So here it can be written as I is proportional to V, so that current is depends on the potential difference. So it can be written as V is equal to IR. R is the resistance of the conductor. Okay. So here this statement we called as Ohm's law. Isn't it? That is current is directly proportional to potential difference across the ends of the conductor. Okay, that is what we call Ohm's law. So next, yeah, we can differentiate two kinds of devices. One is ohmic device, another one is non-ohmic device. So yeah, how we can differentiate ohmic and non-ohmic devices? So which devices obeys Ohm's law? That kind of devices we call it as ohmic devices. Another one is opposite of that, not obeys Ohm's law, called non-ohmic devices, isn't it? So yeah, we can study the IV characteristics of the this ammeter and voltmeter. Okay, that means when we plot the graph current versus volt, so we study the characteristics of voltage and current, we get the graph. That means we get the linear line. That means straight line. So once we get the straight line from the graph, so that indicates the device obeys Ohm's law. Okay, for example, ammeter and voltmeter. Ammeter, which is measure the current, voltmeter, which is measure the voltage. Okay, so that is what we call ohmic devices. Okay, so next another kind of device, non-ohmic devices, what they are says here. That means we are not obtaining a linear line, we are obtaining a non-linear line. So this kind of IV characteristics we call it as non-ohmic devices. That means, so which devices not obeys Ohm's law we call it as non-ohmic devices. For example, semiconductor diode like Zener diode, normal diode, tunnel diode, like that, and transistors. Okay, so these are the examples of non-ohmic devices. Is it right? Here normal Zener diode, LED, transistor. Okay, this is the transistors, and this is the what we call the solar cell. Okay, like that. So these are the non-ohmic devices. Okay. So next we go for another thing, resistance of a material of a conductor. That is how the resistance arises. The resistance is nothing but with the ratio of voltage and current. That means it is defined as the ratio of the potential difference across the ends of the conductor to the electric current through it. So this is what we call the resistance. So which the ratio of voltage and current, so that is known as a resistance, isn't it? So from the Ohm's law, I is directly proportional to V, that means current is directly proportional to potential difference. So this one we can write it as V is equal to IR. R is the resistance. So that R, it can be written as R is equal to V by I. So this is what we call a resistance. The SI unit of resistance is ohms, isn't it? So resistance is a physical quantity. Okay, so that we have the unit. That unit is ohm. Ohm is the SI unit of resistance. How we can define 1 ohm? The 1 ohm we can be defined as the resistance of a conductor is said to be 1 ohm when the potential difference of 1 volt applied across its ends produces a current of 1 ampere in it. That means when the potential difference applied across the conductor, it produces 1 ampere of current. So that is what we call 1 ohm, isn't it? So here the ohm is the unit of resistance. The ohm we can define as when potential difference applies 1 volts, it produces 1 ampere of current, isn't it?